Hello students, today we are going to discuss a very useful and I would say extremely important concept related to springs. How the spring constant changes when we combine springs and what happens to the spring constant when we cut a spring into different parts. Now this is a concept that I'll be using again and again in many of my upcoming videos. So I thought it would be better to discuss it separately and understand the physics behind it rather than simply memorizing the formulae. Let's begin. Suppose we have a spring whose spring constant is k, and equal and opposite forces F are acting at its two ends. Now, whenever we discuss an ideal spring, we consider the spring to be massless. Of course, in reality, there is no spring whose mass is exactly zero. When we say that a spring is massless, what we really mean is that its mass is so small compared with the other masses involved in the problem that we can safely neglect it. And this assumption gives us a very important result. According to Newton's second law, that is F is equal to ma, for an ideal massless spring, ma term is zero even if the spring is accelerating. Therefore, the net force acting on the spring must be zero as well. In other words, the force acting at the two ends of the spring must be equal in magnitude and opposite in direction. So that resultant force becomes zero. So if a force F is pulling the spring from one end, the same force must pull the spring on the other end as well. Now suppose that because of this force, the spring gets elongated by a distance x. Then we know from Hooke's law that F is equal to kx or k is equal to F over x. So this is how a spring constant is defined. So this is a basic relation that we are going to use throughout our discussion. Now let us take two identical springs, each having spring constant k, like this. Suppose the same force is applied to each spring. So set of force F here and the same set of force F on the other identical spring. And both springs are ideal. Both springs have same spring constant. So they will elongate by the same amount and call that as x. Now comes the interesting part. Let us connect these two springs end to end. What happens now? So I've connected these two springs here. At first sight, you may feel that something has changed because the force at the junction, this is the junction where two springs connect. The force at the junction between the two springs is no longer visible in the free body diagram. What's happening? These forces are still there, but it's not visible here because now these forces become internal. So only external forces are shown in a free body diagram, though these forces are still there. Each individual spring is still there and is still being pulled by the same force as in this case. So here there are two parts of the spring and both these parts are experiencing the same force as they experienced when they were separated. So here both the parts will elongate by the same amount by which they elongated in this situation. If the elongation was x here, these springs will also elongate x. Each part will elongate by the same amount and the total elongation will become 2x, and therefore the spring constant of this full spring is force divided by its elongation. So that is becoming k by 2. Similarly, if we had three springs and they were joined like this, as we joined two springs, suppose there were three springs, each spring identical in nature, and in that case the spring constant would become k by 3 then. Similarly, for four springs it would become k by 4 and so on. And if we add n identical springs, the spring constant will become k over n. So by adding springs, the effective k reduces by the number, and that number is actually the number of springs that are added. So it's all about adding the springs. Now suppose we cut a spring rather than adding. Now we are cutting a spring into identical parts. For example, we cut a spring into four identical parts and take one part out of it. This is one part. Three parts are still there. This one part will have a spring constant equal to 4k. Now the reverse is happening. In earlier case, we were adding springs and spring constant was decreasing. Here we are cutting a spring and spring constant will increase, the reverse effect. And it will increase by that many times. Here it is 4 because we did 4 parts. If we did n parts of n identical parts of a spring, then spring constant of one part of the spring would become k, that is the spring constant of full spring, into n. So this is the effect of cutting a spring. And what about these 3 parts? Every part will have a spring constant 4k as we have for this part. Now these 4k, 4k and 4k, these 3 4ks are added. So when these 4ks are added, the effective constant will become 4k by 3. So this is how effective spring constant changes on adding springs or on cutting a spring into its parts, identical parts. When a spring is cut into n equal parts, the spring constant of each part becomes n times the spring constant of full spring. So cutting a spring makes each individual piece stiffer. It's hard to elongate this part as compared to the elongation of full spring. Full spring can easily be elongated, while a small part of that spring is very tough to elongate. Means a larger force will be required because its spring constant has increased now. So adding a spring reduces spring constant, cutting a spring increases spring constant. So in one line, we can say that when you add identical springs, spring constant decreases by that number of times. And when you cut into n identical parts, then spring constant of one part becomes n times. Okay.